Now we want to look at the ideal gas equation in a more quantitative manner. The first thing we need to look at is the actual formula, which is PV equals nRT. P is the pressure, it's typically in units of atmospheres. Volume is in units of liters. N is for moles. R is the ideal gas constant, and T is the temperature, which must be in Kelvin. Now, if you notice at the bottom, we have the value of R. This is a constant, and what we see is the value is 0.08206 liters atmospheres per mole Kelvin. So if you're working a problem and you forget what the units should be, you can always look at this as a reference, because remember, we need our units to cancel out in order to get to the correct units for the unknown value for which we are solving. So let's look at an example of how the ideal gas equation is used. So determine the volume occupied by 2.34 grams of carbon dioxide gas at 0.97 atmospheres and 25 degrees Celsius. Well, knowing this is a gas and we're given various measurements for a gas, that's always a clue that we're going to use the ideal gas equation. So let's look at the ideal gas equation and see what we have and what we need to find. So the equation is PV equals nRT, and we're going to go through each variable to figure out what we know and what we don't. So the first variable is P, which is for pressure, and what we see is that the pressure is given 0.975 and it's in units of atmospheres, which is exactly what we want. We notice there's no volume because that's what's being asked for, because the question says determine the volume. Next, we see that the amount of our sample is in grams, but we must put the amount in moles, so we're going to have to convert from grams to moles. The value of R is a constant, 0.08206 liters atmospheres per mole Kelvin. So we'll use that in the equation. And then we have our temperature, which is in degrees Celsius, and will have to be converted to Kelvin. So first, let's look at converting the grams to moles. So we see we have 2.34 grams of CO2. We're going to use the molar mass of CO2, which is 44.01 grams per mole. And we will find that we have 0.0532 moles of our CO2. Now we need to look at the temperature, and we're going to add 273 to the temperature in Celsius and get 298 Kelvin. Notice the equation has 273.15, but because my value in Celsius did not have any decimal places, I did not need to include that, because even if I had added 273.15, I would have had to round to the least number of decimal places, so I will be back at 298 Kelvin. Now I can start plugging in my known values into my equation. So I have my pressure and volume. My volume is my unknown that I'm solving for. I plug in the moles that I calculated from the mass of the sample. Then I add in the ideal gas constant. Note there are several versions of the ideal gas constant. This is the one we will be using. They're all equivalent, but they have different units associated with them. And then we put in our temperature in units of Kelvin. Now we just rearrange and solve for the unknown value for the volume, and we get that the volume is equal to 1.33 liters. So there's lots of different problems we can do using just the regular ideal gas law to solve for our one unknown. However, sometimes we're looking at scenarios where there's two conditions, some initial and final, or condition set 1 and condition set 2, and in those cases it's more useful to use what we call the combined gas law. So notice this equation is just a rearrangement of the ideal gas law. So if we have PV equals nRT, and we divide both sides by NT, what we end up with is R equals PV over NT. And so what I can do is look at PV over NT in their initial conditions, which is here on the left, and then look at PV over NT under final conditions, which is here on the right. Both of these left and right are equal to R, so they must be equal to each other. Sometimes you'll also see these designated as 1 and 2. So you might see P1V1 over N1T1 and P2V2 over N2T2. The notation doesn't really matter. The key is that we have an initial or starting set of conditions and some final set of conditions. And we have to watch to make sure we get to keep the data sorted correctly. So let's look at an example where we use this combined gas law. So cyclopropane C3H6 is a general anesthetic. A 5.0 liter sample has a pressure of 5.0 atmospheres. What is the volume of the anesthetic given to a patient at a pressure of 1 atmosphere at constant temperature? So we see we have two sets of conditions. So the first thing we want to do is write out the combined gas law. So P1V1 or P initial V initial over NITI is equal to PFVF over NFTF. Now, many times when we're looking at a combined gas law, we see that some of the variables are actually constant. And when variables are constant, they can actually be canceled out. So when we look through this problem, one, it tells us explicitly that we are at constant temperature. So if Ti equals Tf, that means they're going to cancel out in the equation. Just as if they were 2 and 2, they don't actually change anything about the quantitative values in the equation. We also see that the way the problem is written, it says an explicit 5-liter sample. It doesn't mention either adding or removing any of the cyclopropane, which means we can also assume that moles are constant. So what we're left with is PI-VI equals PF-VF. So we say, well, PI is equal to 5.0 atmospheres because that's given in the problem, and VI is 5.0 liters, which is also given in the problem. Then we can look at our final conditions, and we see our final pressure, which is given, is 1 atmosphere, and the final volume is our unknown. The most challenging part of the combined gas law problems is making sure we keep the initial conditions all together and the final conditions all together. Now we can plug in the values we know. So we know our pressure and volume initially, and we know our final pressure. And we're going to leave VF in because that's the unknown we're solving for. And now we can say VF is equal to 25 liters. Let's look at another example using the combined gas law. Different variables involved, and including a temperature, which is not constant. So we're going to have to keep that in the equation. So the first thing we're going to look at is let's collect the data we have. We see we have the initial volume, which is 2.6 liters, and the initial temperature, which is 22 degrees Celsius. And we're going to have to convert that to Kelvin because anytime we're using temperature in a gas equation, we must convert it to Kelvin. So we add 273. Now we look at our final conditions. We do not know the final volume. We know that the final temperature is 36 degrees Celsius, which is equivalent to 309 Kelvin. Now, we see our pressure and our moles are constant because there's no mention of them changing, and unless it tells us something about them changing, we can get to assume that they are constant, which means when we write our combined gas law, we will be able to cancel out the pressure and the moles because they are the same on both sides of the equation. So we have PI-VI over NITI equal to PF-VF over NF-TF. Now we can look that the pressure and moles are both constant, so we can actually cancel them out on both sides of the equation. So what we're left with is VI over TI equals VF over TF. Now we can substitute in our values that are given in the problem. So we have 2.6 liters over 295 Kelvin equal to the volume final over 309 Kelvin. We can rearrange and solve for the final volume, and we get 2.7 liters. Remembering that volume and temperature are directly proportional, the temperature goes up, the volume is expected to go up.